Machines that build machines. It's a curious paradox. Whenever you consider something that builds itself physically, it could conjure thoughts of an infinity loop or an M.C. Escher painting, the never-ending loop of technology. The extreme ultraviolet EUV lithography machine, a marvel of modern engineering, etches patterns onto silicon wafers with unparalleled precision, giving birth to the microchips that power our world. A machine so advanced, so intricate, that it holds the power to create the very building blocks of our digital age. It gives birth to the state-of-the-art in semiconductors. Indeed, the future pulled forward to today. As we marvel at the bleeding edge of technology, we often overlook the humble components that make it all possible. Inside every EUV lithography machine, a symphony of legacy technologies plays out, from power management diodes to analog circuits. These unsung heroes, though less glamorous than their cutting-edge counterparts, are the backbone of innovation. In the wake of the COVID-19 pandemic, the world has witnessed the fragility of global semiconductor supply chains. Black swan events have exposed the dangers of over-reliance on a single source, leading to shortages that ripple across industries. It is a stark reminder that the latest and greatest cannot exist without the tried and true. As we navigate this era of rapid technological advancement, let us not forget the importance of balance. The yin and yang, of old and new, of leading and lagging edge, are forever intertwined in the dance of progress. The lead guitar and vocals may provide the memorable moments in your favorite songs, but have you ever heard a song without the drums? Modern architecture can inspire and awe, but ever tried to build a house without a concrete foundation? Trips to the zoo to visit the tigers provide moments of wonder. What would happen if the protective glass was removed? Remember that next time you marvel at the latest gadget or gizmo. Take a moment to appreciate the unassuming components that make it all possible. For in the grand scheme of innovation, every piece of the puzzle matters, no matter how small, outdated, or seemingly invisible. How does microchip technology provide the critical components for producing microchip technology? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Our guest today is Leon Gross. Leon is Vice President of Microchip Technology. He runs the Discrete Products Group. He joins us today from our global headquarters in Chandler, Arizona. Welcome, Leon. Thank you for joining us on Beyond the Microchip.
Thank you for having me.
In the intro, we briefly talked about the advanced technology nodes that propel us to the frontier of Moore's Law and provide some juicy headlines that sell newspapers. But there's more to it than that, and we could be missing a key piece of the story. You want to tell us about it?
Well, you mentioned it earlier with the EUV equipment. It's very interesting that our technology, some 20, 25-year-old technology that's been around and well-worn, well-used, that people don't even think about, is what powers these machines that allow us to do these technological innovations. You mentioned the supply chain shortages. When we learn through shortages where things go. Mm-hmm. And so we saw a deep need for power, and our discrete components allow engineers to go ahead and design power supplies that are used in these very, very advanced pieces of equipment. It's not just in lithography. We power various pieces of equipment in semiconductor capital equipment that's used in the wafer fabs to manufacture these things. So, as you mentioned, all those leading edge technology nodes, the stuff that people talk about very excitedly, 5 nanometer, 3 nanometer, even 7 nanometer still, none of that happens without this 25-year-old technology providing power into these tools. And so we don't necessarily make the high density memory chips. We don't necessarily make the leading edge microprocessors that some of the other companies do. But without our products, they can't make those things, and they can't introduce those advances in technology. So, it's a very interesting loop of utilizing the old in order to be able to innovate the new.
Yeah. I've used the analogy in the opener of you can't have a good song without the drums. I like to think of it sometimes as perhaps the picks and shovels during the gold rush. Gold is great, but you got to get it out and you got to get it somewhere to where you can actually do something with it. And there are these lesser pieces that don't seem as complicated don't seem as advanced, but they're absolutely critical. Even in some of the most advanced technologies, like, say, space exploration, we're still going to have discrete components and some older technology there because one is it's a cost factor, right? But it's more about reliability, right?
Yeah, it is. Space in particular, the general long-term space programs that are out there, it's very hard to go out if something happens in a satellite to go send out people to fix that satellite out in space. So they want to use products and technologies that are tried and true that they know are going to give them the reliability that they need. We actually see the same thing in terrestrial applications, though, too. Mm-hmm. You know, about 90% of big data and things like social media actually don't go through satellite communication. There's still too much of a delay, a latency to transmit and get it back through the satellites. So they actually go through undersea cables. And those undersea cables include our products in order to help keep those the signal integrity and to keep the signals moving through those cables. Mm-hmm. So it's another application over and above the semiconductor capital equipment where they're using older technology nodes in order to enable things that we all think are very exciting and cutting edge technologies now. But having that reliability, again, the cables at the bottom of the sea, very difficult to go and repair those things. So they want that high reliability that they get from our components.
Right. And there's also a factor of products that need to be out there for a long time. So that can't send a repair guy. That's a good thought to bring on. When we talk about discretes, are they a category by themselves?
Well, discrete by definition means individually separate and distinct. In the industry, it tends to mean individual devices that are manufactured to perform a specific function. So a single diode or transistor. Mm-hmm. You know, the leading edge microprocessors in that consist of hundreds of thousands or millions of transistors, and they aggregate all that to be able to do the really cool things that they do. My components are individual single components, but what they allow is for a flexibility for an engineer that's doing design work. Having those discrete components allows them to figure out exactly how they want to do things, and it gives them a flexibility that they don't have if they have something that's fully integrated.
Right. So you're talking about brute force. Is that the idea that the Ferrari will take you down to the store, but you don't need a Ferrari to do that?
Kind of, yeah. It's you can have a car without seats, but it works. You know, it's a lot easier to drive if you have the seat in the car.
Got it. Okay.
And so, you know, that seat is a discrete piece of that overall.
I see. Okay.
Car.
So where do they fall in the technology spectrum?
As I've mentioned a couple of times, these are older technologies. You know, some of the technology stuff that we do is actually approaching my age, where you've got things that are 30 or 40 years old. Some of the technologies we use are newer. They're only in their 20s. So
babies by comparison.
Yeah. So they tend to fall on the lower end of the technology spectrum. But again, you don't get the high end of the spectrum without being able to utilize these in order to get there.
Mm-hmm. So, of course, there's more to it. Is there a larger system at work?
There is. In most cases, there's a balance in systems, right? You have various levels of integration and various levels of integrated and discrete products throughout an entire system. And so I've been hearing rumors for years that discrete products will stop being used. And I can tell you that it's not true.
Not going to happen.
It's not going to happen. We're always going to need the ability to be able to adjust and to be able to adapt. And in many cases, it's by combining the older technologies and the new technologies in order to be able to push things forward.
So we talked in the opener about EUV machines and some advanced technology nodes. Where would some of the components that we're talking about fit in that process or processes like that?
So our microchips, discrete RF MOSFETs, are used in the power supplies. They provide power in these applications. Mm-hmm. All of these tools are very complex, and like the floor space that's taken up for this EUV machine is huge. And usually it requires a whole system of various cranes and different things in order to even place it in the facility that it needs to be in.
Yep, bolted to the floor.
It's bolted to the floor, but they keep the cranes overhead. They're built in because if they ever have to work on the tool, they have to lift pieces of it up so that you can get to where the power supplies are. Mm-hmm. So they're very complex, very expensive, and they perform some very key functions in enabling all these other technologies that are out there. But ultimately, without power, it's just a really, really big, you could use it, to anchor boats. Mm-hmm. Without power, it doesn't do anything. It just takes up a lot of space and costs a lot of money.
Probably something that people take for granted is that you have to turn it on.
Right. And most people don't think about it. They have their latest gadget. They just pull the gadget out, they play with it, do whatever they want. And they don't think about the fact that you got to have power. You got to be able to turn these things on. And that's where we come in. We provide power. That older technology is very robust. And so we make it so that instead of having a big building full of boat anchors, you now have a wafer fab where you're able to manufacture the leading edge technology and be able to enable, your whatever you have on your phone, your laptop, your car.
So the idea is these tiny components that are individual, the seat in the car, which I think is a great analogy. If you were to crack open a fairly advanced device like the latest iPhone, for example, you're probably looking at hundreds of components in there. And then some of them are really, really impressive. The M2 chip, the M3 chip. And then right down at the bottom is where you plug the power cord in to charge it. There's a very critical component right there that probably doesn't get a lot of the love that it needs.
That's true. In all of the various gadgets that we have, they do have discrete components as well. So we put the components in the larger tools that are used to make these things. Mm-hmm. They also go into the smaller tools. There's discrete components in the lighting systems of your car. The taillights now, when you look at the taillights of a car, mm-hmm. it's an array of LED lights that are in there, and they have discrete components that are linked up to each of those LEDs that help moderate the power. So, there's discretes that are used all across the board, a lot of it in power applications, but there are other applications for it as well. But they're very key to, again, enabling all of these technology.
Right. Yeah. So what devices do you think apply to the applications we've been talking about today?
Well, the RF MOSFETs are just one of the pieces that we have. We have
about radio frequency RF?
Yeah. So in general, when I say RF, I'm talking about the lower end of the RF spectrum. Mm-hmm. So we're talking about things that are in the 100 megahertz, 150, 200 megahertz range, as opposed to, I do have discrete components that are used in RF communications that go up into, 60 gigahertz. Mm-hmm. But these, in the power applications, they tend to be on the lower end of the RF spectrum. And they're used in a lot of tools, medical applications as well, mm-hmm. where they need to generate high levels of power. So MRI machines, for instance, are one of those tools where they need high levels of power. So they use these products in the power supplies for those as well. That combination of the frequency and the power allows them to do different things for those various applications.
Any key products in the catalog?
In our catalog on the RF products, we have several families. So anybody that's interested can go check it out. And we categorize them by power and frequency cable.
Okay. All right. And where could we send them if somebody had a use case for this technology? Are there any videos or reference designs? Is there a link on the website?
There is. You go to the Microchip website. Mm-hmm. From there, if you look up RF MOSFETs, you can find information on industrial and medical applications that I've mentioned previously, along with some reference designs for those particular applications as well.
Any predictions for the future of discrete products or how the technology could enhance the human experience like we're talking about today?
I mentioned before that discretes aren't going away. I moved actually from the microcontroller world into the discrete world about 25 years ago. Mm-hmm. And at the time, I had many people come and give me their condolences because they said, man, your career's over. Discretes are going to go away and you're not going to have a job.
What would they go away in place of? What was their...
Well, you can integrate, so ICs are integrated circuits, right, where they bring all of that stuff in. But again, integration in and of itself doesn't enable the creativity that you need. And a lot of times you can't integrate at those higher power levels.
Right.
So they said stuff's going to go away. And here I am a few years later, still have a career, and discretes are still there. But what I'm seeing is that there are new technologies that are coming out. So silicon carbide, for instance, or gallium nitride.
Yep.
So we're seeing additions to the discrete portfolio. So instead of discretes going away, actually the toolbox that you have to play with is becoming larger.
Newer and better seats.
Indeed, yes.
So I'm interested in this idea then. So an integrated circuit would allow, are we talking about system on chip? Or are we talking about something that's extremely complex that would ostensibly replace it, which we don't think is going to happen?
So there's integration can be achieved a number of different ways. You can do it directly in the design. So as you build your integrated circuit, you're building different areas and different functionality into the actual chip itself. You can add functionality through having different chips co-packaged together, or you can have, so it's a variety of levels of integration depending on how you want to approach it. The problem is when you start integrating things too much together, you drive increase in size. So the chips keep getting bigger and bigger and bigger.
Yep.
And that makes it cost more to do that.
Right. Limited board space.
Yeah. So there's limits, but we keep moving the bar for the limits, Moore's law in that. It keeps changing. But there's limits to what you can do from a power perspective too. So you have power, you have heat conduction, heat loss, and things like that. So you see a trend towards trying to integrate everything into the circuit for a while, and then eventually you see where they start spitting stuff back out again. And so they decide that now in order to get maximum efficiency, you can take these pieces out, do them separately. You can get better performance out of those functions then. And when you put them together discretely, then you end up with a much better overall system performance.
Right.
So there's always trends where things are cyclical, and people get the idea that they want to do everything all together in one chip, and then it goes the other way after a while again. And I think that engineers are really creative, and so they're always going to figure out other ways to do things. And that's where we see these cycles come where they can have an advance due to the new technology in wafer fabrication that allows them to do new and better things at the silicon level. So they might integrate some things in for a while, but then later on, as technology changes again, you get focused on different things. So then you start to disintegrate some of it back out again. It's going to continue like that.
So as Moore's law chugs on relentlessly, we've also got some material innovations, some material sciences. You mentioned gallium nitride, you mentioned silicon carbide. You think there's only just going to be more discretes for each of those emerging technologies?
So I think there's going to be discretes, and they're looking at how do they integrate the silicon and those wide bandgap materials together. So I mentioned you put chips together, co-package them. They're going to be looking for ways of doing things like that. They're going to look for ways to process it simultaneously. So, it'll drive new innovations in, how not only how they process it, but the base materials that they use, and then packaging technology, of course, beyond that.
So it still comes back to flexibility and adaptability?
Yes.
Okay. Any final thoughts?
Well, so I've been talking about how great discretes are and what they allow you to do from a flexibility standpoint. As a company in Microchip, we have those leading edge technologies as well. So we have the discrete and the power technologies. We have the leading edge technologies. Basically, we can provide whatever level of integration is required for our customers' applications. So if they want something that's total discrete implementation, no problem, we can do that. If they want to do something that combines the two, we can do that. If they want the latest leading edge technology fully integrated, we can do that. So it's It's the great thing about being in a company like Microchip is whatever our customers need, we can help provide them with the technology to enable their innovations.
Mm-hmm. That gets to that total system solution concept, right?
Yes, absolutely.
Yeah. So you mentioned that. So we've got 8, 16, 32, and now 64-bit microcontrollers. We've had a number of guests on in recent episodes that are talking a lot about silicon carbide. We just did gate drivers today. We're talking a lot about how a lot of power management recently has been coming about, but it still comes down to no matter how advanced your logic or your memory is, you're still going to have other components that are going to be in support roles, critical, but maybe not as high exposure. And it's important that any system design, or even to go all the way out to the level of the user, you can do all of these things on an iPhone, but you got to be able to turn it on.
That's right. So the iPhone itself needs to be turned on, and then the individual functions within the iPhone require various levels of power. Mm-hmm. And so, we do, like you said, up to the 64-bit microcontrollers and microprocessors now. Those are really great, super cool technology. But there's a number of power rails that provide power to those chips. Mm-hmm. And again, that's where the other technologies that you have, maybe something on the analog side that might not be completely discrete, but still required in order to support this. So you need a variety of technology levels to make any of this stuff work.
Right.
And so everybody gets excited. It's the shiny new thing. Mm-hmm. Everybody wants to look at the shiny new thing in that. But don't forget, there's a whole lot of other support things that go on behind that in order to make it work. And, we have that here.
Mm-hmm. Along with support and services, and we kind of put the whole package together, right?
Absolutely.
That was great, Leon. Thanks for joining us.
Thank you.
Leon Gross is a vice president at Microchip Technology. He runs the Discrete Products Group. He joins us today from our global headquarters in Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.